Hey, so just gonna make sure that I am live, although I am pretty sure it is working. It's been working consecutively um, this week. So just going to check the audio. It actually seems like the audio either isn't working or is too low. Glad I checked. So I can actually tell the audio is too low. It's actually quite odd. I can tell right here, which is weird though. I will. It is locked, so there shouldn't be any way for that to happen. I'll turn it up though. Let's turn it up to around here. See how that goes. Usually takes about 10 seconds for the monitor. Oh, that's much better. I will lock the volume here. Okay. Well, I'm glad I checked. Let's get into things. Good morning, everyone, and welcome to Tea with Chloe in the morning. I got tea here. I got some panettone, some Christmas bread. Got some raisin bread with all natural peanut butter and some jam, some strawberry jam, I think, or raspberry. I can't remember. Um, got some honey ginger tea, and I have some water. So I am set for the next hour or so. I am the co-founder of the Marma J Foundation. We work to leverage Web3 tech for social good, spread love, support, and positivity in the Web3 space. More tangibly, I am one of the directors of Marma J Labs, which is an up and coming nonprofit in Antigua. Working to educate and support, I guess, innovative tech businesses in the Caribbean region. And in that, I'm also kind of supporting Uncloak. And Uncloak is actually specifically what I'm doing here today. So Uncloak, on the right side of my screen, is a website to start. We can kind of go to the front page. It is a community-maintained knowledge wiki experiment aiming to increase the accessibility of cryptography for developers, researchers, and everyone else. So we're going to keep it really simple. We're going to just say that's what Uncloak is for now. And as you get involved, if you even care beyond this, you can kind of go to uncloak.org and read this README on your own. In Uncloak, though, there is a course for cryptography engineering in Rust. We are on session 8 currently, or 9, session 9 currently. But I am currently kind of working my way through session 10. In the session 9 notes, there is actually a question to use the internet, find at least one method used for nonce generation besides a counter. Describe this method for nonce generation in the Discord study group main channel. So I'm going to do that after this stream. So I'm going to stream for a bit, like an hour and a half. I'm going to go do this question from number 9 and submit it into the Discord. And then I'm going to kind of start looking at chapter 10 notes, not chapter 10 solutions. So the exercises are at the bottom of the notes. So, recalculate the extended Euclidean algorithm for the, inverse of 397 in the group modulo 2357. So I've got to work at my understanding of the math and how it fits together. I'm understanding the parts, in my opinion, a lot better. But how they fit together and how you kind of write programs to help solve the problems, I'm kind of still working on that. And to do that, I'm reading through and taking notes on this textbook here. Introductions to... Wow, I'm forgetting the name of the textbook already. Introduction to Mathematical Cryptography, ITMC. So we've been taking some notes. We got to the last, I had one stream that kind of got cut short. My second stream, it also got cut short for a different reason. And now hopefully we'll at least get most of the way through chapter 1 now. And if we don't finish chapter 1, then in this stream, and then this afternoon, we will try and get through that. Without further ado, let's get started. We've already taken this definition right here. I don't have very good formatting on my notes, but that's all right. They're just for me to make sure I have what I think is important, and I can look it up later for now. I walked through this in one of the code things I had written from earlier. We went through like long division, and this was a bit confusing for me, but I was starting to understand, where are we? How proposition 1.4c, the proposition right here, is being used here at least. And then Euclidean algorithm, nothing more than repeated division with the remainder. Notice how the quotient and remainder on each line become the new a and b on the subsequent line. So theorem 1.7, the Euclidean algorithm. Let a and b be positive integers with a greater than b. So you always got to have, one of them bigger than the other, and a is, or I guess they could be equal, but that wouldn't really be very useful. But anyways, the following algorithm computes the greatest common denominator of a and b in a finite number of steps. So I guess it's helpful to know that it's not going to run forever in any case, because it's going to find the greatest common denominator. It might be 1, it might be some other numbers, or 1 and the number, but anyways. So let round 0 equals a and r1 equals b, sorry, r1 and r0 and r1, set I equal to 1, and then like divide ri, so the I is the actual round, and you divide ri minus 1 by ri to get the quotient for I. So, I mean, you can look through this yourself. Honestly, I already walked through it. It makes sense, obviously. But I think it is worth taking the time to actually walk through each step of the algorithm, and like see how the code might look. I'm not gonna lie, I just take this generally and put it into like the chat bot and like argue back and forth about getting the algorithm and trying to get the algorithm to give me some code. But I'll probably do that live one of these days. Maybe once the chatbot actually becomes like a paid service that you actually have a license for. Maybe I'll kind of argue with it live on the stream. So there's a proof here, and again, I'm not very good with proofs, so I am going to walk through this proof for just like, very quickly, because I think that the algorithm, while it's, the theorem is quite self-explanatory, the proof and understanding how to write the proofs is very important. So the Euclidean algorithm consists of a sequence of divisions with remainder as illustrated in figure 1.2. Remember that we set R0 to A and R1 to B. So they're saying this is the figure and this is the proof. So they're writing it out visually, how A equals B times this, right? And then B is going to be equal then to R2 with all of, with the quotient plus the remainder 3, and then R2 right up here is equal to this, and it kind of continues to go, and it's just saying that R2's between these two numbers, R3 is smaller than R2, R4 is smaller than R3, and you go all the way down until you eventually get RT, which is the GCD, eventually, right? RI values are strictly decreasing, and soon as they reach 0 on the algorithm, as soon as they reach 0, the algorithm terminates, which proves the algorithm does finish in a finite number of steps. So that's, I guess, the proof that no matter what happens, you will eventually get to this RT, which will give you the answer. So at each iteration of step 3, we have an equation like this. This equation implies that any common divisor of Ri minus 1 and Ri is also a divisor of Ri plus 1. And similarly, it implies that any common divisor of Ri and Ri plus 1 is also a divisor of Ri minus 1. Hence, the greatest common divisor of I minus 1 and Ri equals the greatest common divisor. Okay, yeah. Greatest common divisor of Ri and Ri plus 1 for all I, 1, 2, 3, as high as you want to go. However, as noted above, we eventually get to an Ri that is 0, say Rt plus 1, or equals 0, excuse me. Then Rt minus 1 equals Rt times the quotient T, or Qt. So the GCD of Rt minus 1 and Rt equals the GCD of Rt multiplied by Qt, and Rt equals Rt, because Qt is 0, right? And then you have just that times 0. This 0 times this just gives you this. And then Rt minus 1 is Qt. Anyways, but equation 1.2 says that this is equal to GCD Ro and R1, i.e. to GCD A and B, which, oops, I don't know why. The last non-zero remainder in the Euclidean algorithm is equal to the greatest common divisor of A and B. It remains to estimate the efficiency of the algorithm. We noted above that since the Ri values are strictly decreasing, the algorithm terminates, and indeed, since R1 equals B, it certainly terminates in at most B steps. However, the upper bound is far from the truth. We claim that after every 2 iterations of step 3, the value of Ri is at least cut in half. In other words, they're claiming that Ri plus 2 is less than a half Ri for all I, 0, 1, 2, all the way up. We prove the claim by considering 2 cases. Case 1, Ri plus 1 is less than or equal to half Ri. We know that the Ri values are strictly decreasing, so Ri plus 2 is less than Ri plus 1 is less than or equal to half Ri. Okay, I'm not going to read through all these wonderful cases, but they're trying to show this and then prove this. They're ducky T divisions, and they're leaving it for us to prove. Or this is the proof, sorry. For theorem. So again, I'm not good with proofs because I feel like I don't have very much patience for them. I can read through it, I can understand it, but the patience of actually writing through it and doing it myself, I need to work on that. Remark 1.8, we proved that the Euclidean algorithm actually, this is the note that I want to take, just so that I can maybe I can type in Euclidean algorithm terminates, and then I'll find. I'm trying to get what note I might need to go with that. Hence, if 2 to the k is greater than or equal to b, then okay, which forces this to equal 0, and the algorithm terminate. In terms of figure 1.2, so we have t plus 1 is less than or equal to 2k plus 1, thus t is less than or equal to 2k. Further, there are exactly t divisions. So the Euclidean algorithm terminates in at most 2k iterations. Figure 1.2, there are t divisions. So t is the number of divisions. I think I need both of these. I think I need the value of RT plus 1 is 0, so we have t plus 1 equals, okay, so you take out the plus 1s, and thus, okay, let's see if this makes sense. Let's do this. Number of iterations. Okay, I do want that to look somewhat normal. I don't know why that looks weird. Oh, it'll be fine. The number of iterations is going to be less than or equal to 2k, which equals to 2k minus 1 plus 2 is less than 2 log 2b plus 1 plus 2. The whole substituting and all that. I should probably do this math later. And there's the actual. Yeah, that's weird. So plus 2 and plus 2, but it's actually plus 1. 2 log 2b plus 1. Okay, so this is the actual note, and I feel like what I took above was just trying to get the math down as well. Okay. I don't know why. Yeah, whatever. Notes are looking really weird, but such is life. This estimate can be somewhat improved. It has been proven that Euclidean algorithm takes no more than 1.45 log 2b plus 1.68 iterations, and that the average number of iterations for randomly chosen A and B is approximately 0.85 log 2b plus 0.12. So the actual range is better if you do more improvements. Maybe I'll just go. Oh, that's why? That's weird. That's good enough. Remark 1.9, one way to compute quotients and remainders is by long division, as you do on page 12. You can speed up the process using a simple calculator. The first step is to divide A by B on your calculator, which will give a real number. Throw away the first part of the this one was weird. I liked reading through this. It helped me understand a bit, but I found it very weird. Throw away the part after the decimal point to get the quotient Q, and the remainder can be computed as remainder equals A minus B times this quotient that you got. So for example, I'll go quickly through this part. if A equals this large number to the left and B equals this large number to the right, then A divided by B is 86 point this, these decimals. So the quotient is 86, and the remainder is this, this equation here. So A minus B times the quotient. So you have A here minus B here times the quotient, and then you get 15909, which is the remainder. If you just need the remainder, you can instead take the decimal part, also sometimes called the fractional part of AB, and multiply it by B. Continuing with our example, the decimal part of A divided by B is this decimal, and multiplying by 27573 gives this number here, which is the same as up here, which is super cool. And then some random rounding, which is like, okay, apparently you just round it off. After performing the Euclidean algorithm on two numbers, we can work our way back up to the process to obtain an extremely interesting formula. Before giving the general result, we illustrate with an example. So we did this already earlier, right? So again, this is what we already saw from above. It's saying now we let A equal, 2024, B equals 748. So the first line would say that 528 equals A minus 2B. Again, from up here. We substitute this into the second line. Again, this is now getting to substitution, where we're substituting from here, the second line here, to get B equals A minus 2B times 1 plus 220. Again, 1 plus 220, A minus 2B, because A minus 2B is up there. Sorry, up there. Anyways, you go through each line like that. And it is just following along with this. So if you, again, go to the textbook, you can kind of see how that would work. And it's saying, okay, we found a way to write the GCD as a linear combination of A and B using integer coefficients. So -7 times 2024 and 19 times 748 equals 44, which is the GCD. And the idea is that you started with these two numbers, 2024 and 748, and you're able to find the GCD in another way and express them in using, integer coefficients. So that's kind of the interesting part here, is how you could take your A and your B, and you can find your GCD with these other integers that are being multiplied by you're starting off A and B. So what are these other integers, and how do we find them, and what's their use case, I guess, is kind of the extended Euclidean algorithm, I guess, which is like the real fun part. So then you get to, the extended Euclidean algorithm. So let A and B be positive integers. So this is A, this is B. They are positive integers. Okay, we're good to go. So you have AU plus BV equals the GCD of AB. So this must be U, and this must be V. Always has a solution in integers UV. So then they give you an actual algorithm to find the solution, which is super cool in my opinion. But anyways, if U0 and V0 is any one solution, then every solution has the form. To get U, you can get the U0 plus B times K over the GCD of AB. V0 minus, and this is why it's important to have A, B large. There you go. This is why I did it. A larger or equal to B. That's why it's important. So you can remember that one of them is plus, one of them is minus. This is A, this is B. And for some element, you know, where K. Oh, I'm getting like connection issues. Okay, seems like maybe we're back. Okay, seems like we're back. We can solve the first line for R2, AB, Q1, Q2. Okay, so yeah, you're just doing the same thing we just talked about. The key point is that R4 equals A times, they're just saying that this is U and this part here is V. Okay, where U and V are, I already read through this, I just, sometimes I forget what's saying what. It does not matter that the expressions for U and V in terms of Q1, Q2, Q3 are rather messy. I think this is the point. It's just trying to simplify things and say it doesn't matter what all this stuff is. You just kind of take it all together and this is your V. And it doesn't matter what all this stuff is, just take it all together and, sorry, take it all together and it is your U. I think that's just the main point, is that you can just group all of the elements together to get your U and your V, because you know the GCD, yeah, of A and B. Eventually we get to RT, right? The same RT from before equals A times U plus B times V for some integers U and V. But RT also equals GCD. That was the point. Above, we already said RT equals GCD, which was 44. And if RT also equals A times U plus B times V, and then you completed your proof, because you know that the GCD also equals A times U plus B times V, which we, again, already knew from above. It's just giving you the proof, which is why I got confused, because it was just a proof. And be thorough. A and B be integers. We say that A and B are also be prime if the GCD is 1. More generally, right, you have AU and BV, but the GCD just equals AB, because, you know, it's just 1. I seem to be having some sort of 45% dropped frames. That is a lot of dropped frames. But it says I'm green right now, so I'm just gonna keep going. For example, we found earlier that these T numbers divided by 44, we obtain equals 1. I mean, of a linear combination of 16 and 17 that equals 1. Okay, this part right here, I think is something that, like, I need to just remember and read. Although the stream quality must be terrible. I'm not sure exactly what's going on. I'm dropping like 30% of my frames. But this line here, and super important. So this whole idea of, you know, we figured out that these two were relatively prime because we got this 44. So that was the first part. Remember, I showed the code from week 8 where I took two numbers and was able to find the GCD. Then it's saying, okay, all you have to do now is divide both sides by 44, which is super interesting because, again, you're just trying to get this to 1. And then because it goes down to 1, it's saying they're relatively prime, which is like, yeah, anyways. So the point is that you can now take, because there's no decimals, there's no remainders, it's just you get an actual, you get whole numbers here.